Our world is bathed in light. This light comes from our magnificent star, the Sun. It travels millions of kilometers through space. It brings warmth and life to our planet, and it holds a vast, untapped power. Humanity has long looked to the skies for inspiration. Now, we look to the Sun for a cleaner future. Our need for energy is growing. We seek ways to power our lives without harming our precious Earth. Behold, the solar panel. A silent guardian, often seen on rooftops, or spread across fields in great, shining arrays. These panels are more than just objects. They are a promise of clean, renewable energy. They drink in the sunlight and turn it into electricity. This electricity can power our homes and run our cities. It is a quiet revolution happening all around us. A shift towards a more sustainable existence on this beautiful planet. Join us as we explore this incredible process. Our journey starts with sand, or to be more precise, quartz sand. This sand is rich in silicon dioxide, often written as SiO2, silicon, the second most abundant element in Earth's crust. It is all around us, beneath our feet, in the rocks, in the soil, and in these tiny glittering grains. This is the very foundation of our solar panel. The raw ingredient, plentiful and waiting, a gift from the Earth itself. The first crucial step is to free the silicon, to separate it from the oxygen it is bound to. This happens in a powerful furnace, a process called carbothermic reduction. The sand is mixed with carbon, often in the form of wood chips or coal. This mixture is then heated to incredibly high temperatures. We are talking about temperatures around 2000 degrees Celsius. Inside this intense heat, a chemical reaction takes place. The carbon pulls the oxygen away from the silicon. The oxygen atoms leave the silicon dioxide. They combine with the carbon, forming carbon monoxide gas. What remains is silicon, but not yet in its purest form. This product is known as metallurgical grade silicon, or MGS. Its purity is around 98 to 99%. The next stage will push the boundaries of material science. The silicon we have so far is good, but not perfect. For a solar cell to work its wonders, it needs silicon of extraordinary purity. We are aiming for something called 6 nines purity. That means 99.9999% pure silicon. This ultra-pure silicon is often called electronic-grade silicon or polysilicon. One common method to achieve this remarkable feat is the Siemens process. First, the metallurgical-grade silicon is ground into a powder. This powder then reacts with hydrogen chloride gas at high temperatures. This reaction creates a volatile gas called trichlorosilane, or SiHCl3. This gas now carries the silicon atoms, but many impurities from the MGS are left behind. The trichlorosilane gas, now much cleaner, is then distilled. This distillation process removes even more impurities. Finally, the highly purified trichlorosilane gas is passed over heated rods made of pure silicon. In this hot environment, the gas decomposes. The pure silicon atoms deposit themselves onto the rods. They grow, layer by layer, forming large chunks of polysilicon. We now have solid silicon of incredible purity. These silvery crystalline chunks are ready for the next stage. The chunks of ultra-pure polysilicon are now ready. Their destiny is to become a single, perfectly ordered structure. This is achieved by melting the polysilicon. It is placed into a special crucible, often made of quartz. This crucible is then heated in a furnace. The temperature climbs beyond 1414 degrees Celsius. This is the melting point of silicon. The solid chunks transform into a pool of shimmering, molten liquid. For the highest efficiency, manufacturers often choose the Czochralski process, or CZ method. This creates what is known as monocrystalline silicon. A tiny seed crystal, a perfect piece of silicon, is dipped into the molten pool. It is then slowly, very slowly, pulled upwards. As it rises, it rotates gently. The molten silicon solidifies onto the seed atom by atom. It copies the seed's perfect structure. The Czochralski process creates a long cylindrical crystal called an ingot. This ingot can be over 2 meters long and weigh hundreds of kilograms. Every atom inside is aligned in a single, continuous lattice. This perfect order allows electrons to move more freely, which means higher efficiency when converting sunlight to electricity. Whether a perfect cylinder or a solid block, the silicon ingot is now complete. It is a dense, heavy piece of highly purified, crystallized silicon, but it is still too large, too thick to be used in a solar cell. The next step is a marvel of precision engineering. The ingot must be sliced into incredibly thin pieces. These pieces are called wafers. They will become the very foundation upon which each solar cell is built. The ingots are first squared off if they are cylindrical to maximize the useful area. Then, the slicing begins. Special saws with diamond-tipped blades or incredibly fine wires are used. These wires, often thinner than a human hair, are coated with abrasive particles like silicon carbide. Multiple wires move back and forth across the ingot. They slowly, carefully cut through the hard silicon. The wafers produced are astonishingly thin. Typically, they are around 160 to 180 micrometers thick. From a single ingot, thousands of these delicate wafers can be cut. Each one must be almost perfectly flat and uniform in thickness. After slicing, the wafers have rough surfaces. They need to be cleaned and polished. This often involves chemical etching and mechanical polishing. The result is a smooth, mirror-like surface. Our pristine silicon wafer is now ready for its crucial transformation. In its pure state, silicon is a semiconductor. It conducts electricity, but not very well. To make it a solar cell, we need to create an internal electric field. This field will guide the electrons freed by sunlight. This is achieved through a process called doping. It involves introducing tiny controlled amounts of other elements into the silicon crystal structure. These elements change silicon's electrical properties. The doping process creates two distinct layers within the wafer. One side of the wafer is doped with an element like phosphorus. Phosphorus atoms have one more electron in their outer shell than silicon atoms. When phosphorus is introduced, it creates an excess of free electrons. This layer is called N-type silicon, for negative. The other side of the wafer is doped with an element like boron. Boron atoms have one less electron than silicon. This creates holes, or absences of electrons, which act like positive charges. This is P-type silicon, for positive. The boundary where the N-type and P-type silicon meet is called the p-n junction. When sunlight strikes the silicon, it knocks electrons loose from their atoms. The built-in electric field at the p-n junction then sweeps these freed electrons towards the N-type side. This separation of charges creates a voltage, an electrical pressure, ready to do work. A single solar cell, even with its p-n junction and coating, is small and delicate. It produces only a small amount of electricity, perhaps half a volt. To generate useful amounts of power, many cells must be connected together. They must also be protected from the harsh outdoor environment. This is where the individual cells are assembled into a complete solar module, or panel. The first step in assembly is to arrange the cells. They are carefully laid out in a grid pattern, often 60 or 72 cells, for a standard panel. Then, thin metal strips, called bus bars and fingers, are added. These are typically made of silver or tin-plated copper. They are screen-printed or soldered onto the front and back surfaces of each cell. These metal contacts act like tiny highways. They collect the electrical current generated by each cell when sunlight strikes it. The cells are then soldered together in series to increase voltage, and sometimes in parallel to increase current. Once interconnected, this matrix of cells needs robust protection. It is encapsulated, creating a durable sandwich. The cells are carefully placed between two layers of a special adhesive material. Throughout this intricate journey from sand to a fully assembled panel, quality is paramount. At every stage, meticulous checks and tests are performed. The slightest flaw, a microscopic crack or an impurity, can reduce a panel's efficiency or shorten its lifespan. Manufacturers invest heavily in quality control. They act as guardians, ensuring that every panel meets the highest standards. The process begins with the raw materials. The purity of the silicon is constantly monitored. The thickness and flatness of the wafers are measured with incredible precision. After the doping and coating stages, individual solar cells are tested. Their electrical performance, known as the IV curve, is carefully measured. Cells that do not meet the required specifications are rejected. Only the best cells proceed to the assembly stage. Once the panel is assembled, it undergoes a battery of even more rigorous tests. One key test is the flash test. The panel is exposed to a very bright, controlled burst of light that simulates ideal sunlight conditions. Sensors measure the panel's power output, voltage, and current. After passing all the stringent quality checks, the solar panels are finally ready. They have been transformed from humble sand into high-tech energy generators. But their journey is not yet complete. They must be carefully packaged to protect them during their travels. These gleaming rectangles of glass and silicon are valuable. They represent years of research and precise manufacturing. Special care is taken to ensure they arrive at their destination unharmed. The panels are often stacked with protective layers between them. They are then secured onto pallets or into sturdy crates. From the factory, they embark on what can be a long journey. Solar panels are a global commodity. They might travel thousands of kilometers by sea, by rail, or by road. They cross oceans and continents, heading towards distributors, installers, and ultimately their new homes. The next crucial stage is installation. This is where the panel is finally put to work. Trained technicians are responsible for this task. For residential systems, panels are typically mounted on rooftops. They are secured to racking systems designed to withstand wind and weather. For large-scale solar farms, thousands of panels might be installed on ground-mounted structures. The panels are then connected electrically. The solar panel, now installed and working, is more than just a piece of technology. It is a symbol of hope, a testament to our ability to harness the immense power of the sun in a sustainable way. These panels are designed for a long and productive life. They stand as silent sentinels, diligently converting sunlight into clean electricity, day after day, year after year. This contributes significantly to reducing our reliance on fossil fuels, which harm our planet. Most solar panel manufacturers offer impressive warranties. Typically, a performance warranty will guarantee that the panel will still produce at least 80% of its original power output after 25 or even 30 years. This remarkable longevity is a result of the robust design and the rigorous testing they undergo. They are built to withstand decades of exposure to sunlight, rain, wind, and temperature fluctuations. This long lifespan makes solar power a truly sound investment, both economically and environmentally. A legacy of light for generations to come.